It provides information about all energy-oriented simulation and all energy-oriented scientific activities. So users, when they want to start simulation and do the computation, need to know what software is available, where it is installed, how to apply for an account on HPC. And these three are organization problems, let's say organization, and the other three are technical problems. They need to know how to access HPC, supercomputer. They need to know how to run the software, and they need to know some details about the HPC environment, especially how jobs are scheduled and how to submit jobs so that they can be run efficiently. So maybe some quick story how supercomputer power was accessed at first. The idea of punched cards is a little bit outdated. It comes from 19th century, but was very popular when first supercomputers were available. Of course, we don't need them anymore. The next was access via console. People needed to go to the supercomputing center, sit in front of the console, the monitor and the keyboard, and they can access the power of HPC. Now there is a little bit better because the console is available remotely. And there's terminal window available from everywhere in the world via SSH. And people can do some actions to access the resources and start jobs. Terminal is still the most popular way to access HPC, but it still has some limitations. You need to know how the shell works, how operating system works. You need to know some commands. You need to know how to prepare job files and how to submit them. So even if terminal is the very flexible tool and most popular tool to access supercomputers, especially among scientists, we need some more, and we prepared Portal. So there are two ways of accessing EoCoE codes now. Maybe not only EoCoE, but every code on almost every supercomputer in the world. You can use it by SSH or by portals. Maybe not all supercomputers can be used by portals, but in EoCoE we have this possibility. On the left side, you see how you need to submit jobs via terminal and via scripts. You need to specify some parameters, bash system parameters. You need to specify some software requirements. Here is OpenMPI, which is used to provide interconnect between the nodes of the simulations, and finally start simulation. On the right, you can see the screen from EoCoE Portal, how you submit jobs. And definitely on the right, you focus on the application itself. You don't focus about technical details, about the batch system, about some maybe not very clear requirements. And you just need to choose an application, specify some parameters, specify some required input files. It's just simple job submission. Of course, Portal has some limitation. You can successfully run some examples. You can run some test jobs, maybe not even tests, but some standard cases. If you need to do some more advanced, probably you need to switch to terminal and SSH script files, but not in the summer school. In the summer school, you just will run some example and test jobs via Portal only. You need to know some information about job scheduler because HPC consists of hundreds, even thousands of nodes. All these nodes are available for users in some organized manner. Users submit their jobs. They put jobs in the queue, and the scheduler needs to schedule jobs, as the name says, to choose the next jobs to run, to assign resources, especially nodes, CPUs, memory, and GPUs, and to start the jobs. And in the context of 1,000 jobs and thousands of nodes, it is not a very easy way to do this, because the scheduler needs to provide resources to all users, not to starve any of them, and need to take care about the priority, some reservations, need to take into account the expected waiting time in the queue, also running time. Depends on the configuration, but usually shortest jobs gain highest priority and run very quickly. So Slurm Workload Manager is used in PSNC to manage resources. And usually when you just log into our access node and need to run jobs, you need to start some Slurm commands and wait for results. In Portal, it is hidden, but maybe a nice picture about how job scheduler works and what are the problems. I found it in the internet, and I see it is very informative. It presents how it works. Let's say that we have a restaurant with a lot of tables, some smaller tables with less number of chairs, bigger tables with bigger number of chairs. Maybe you can have also specialized rooms, smoking rooms, and maybe a vegetarian room, or maybe a room for guests with dogs, or so on. And you have a long queue, very long queue of people that comes to this restaurant and need to be served. Some are families; they need to sit on the same table. Some are individuals; they just don't care about the chair; they just don't do it. Some rooms are reserved for a group of people. Some people are very large groups that need to be put on many tables, and the job of this queue manager is not an easy one, but this is how supercomputers all works too. Job manager needs to assign not people to tables, but jobs to resources. There can be even many entrants, so there are different queues with different priorities and different requirements, and people just know what they need and stand in this separated queue. So when you submit jobs, you need to keep care about servers. Maybe you need to specialize server, maybe send a specialist processor, Intel or AMD, or maybe specific generation of Intel, Haswell, Broadwell. You need to care about storage, how to provide your data to the computation. You need to specify memory requirements. Some simulation require a lot of memory, some are CPU bound, and memory is not a limitation. You need to specify software, because maybe not all software is installed on all nodes. Usually there are some specialized nodes that are dedicated to specialized software. If you need GPU computation, you need to specify it. If you submit not a single job, not a single core job, single CPU job, but many core job, you need to specify some network connection. And of course, you need to provide input data and so on. With Portal, you don't need to care about all of them. So just to summarize the theoretical part, I will show the portal in practice next. EoCoE portal is just the access point to EoCoE. EoCoE is a center of excellence for energy. So if you think about energy and computing, you need to think EoCoE, and you need to find EoCoE portal to access computation, access simulation, and to run simulation in a real environment. EoCoE provides demo resources and demo application with examples to all interested people. So if you are interested in just getting to know how the simulation works, how the software behaves, you just register to EoCoE and can run some simulations. If you will be interested in more usage of application and more advanced computation, you need to contact one of the supercomputing center, maybe PSNC, and you can gain grants to access our resources in more production way. You can run your simulation on bigger scale. The portal is user-friendly, so you don't need to care about all these technical details. You just need to run simulations. And PSNC is provided the portal to hide all the actions necessary below. What they were needed to prepare the resources, to prepare software. Maybe not only PSNC, because authors of the software helped a lot to install, tune, and configure the software. But it is all hidden from the user. User just sits to the portal and run, and don't care about all details. Now we have basic version of SaaS portal is available. It is available for example run and demo simulation. You can submit jobs, manage jobs, get results, and there are templates for demo applications, and details of this application will be shown in our school in the next 3 days. So the service, as I said, is managed by PSNC. You can see Altair supercomputer, and this is the supercomputer that your simulation will run. It is, maybe it was on 85th position in top 500 computers on the world list. It was in the November 2020. Now we are a little bit lower, but in the current list, which was published last week, we are on position 145. So it's still one of the most important supercomputers in the world, and you can access it. Of course, for this demo, you don't need the whole power of this computer, but just you need to use some nodes of it. But if you will be interested in running a bigger simulation, you can contact us, and the same software can be used to run very, very large simulation. So portal has some features that are a registration of users. I will show it next. You can choose a template of application template, set some parameters, run, and then monitor jobs and transfer input and output file. But maybe instead of talking about it, I will show it. I hope you can see my portal screen, not on the presentation. Can you confirm you can see the portal?
Yes, we can.
Yeah.
Okay. So this is EoCoE SaaS portal, and the address you already know, and I will show it on the last slide. And the first screen is this. First, you need to log in, and in fact, you need to register. So first, you need to click login, and then click register, and then fill in the form and submit. I'm already registered, so I will log in. And this is probably not what you see on the first side, because the list of jobs will be empty. But what is the most important for you is this submit a job button, submit a job menu maybe. You need to choose a template. Templates can be chosen from here, or just submit job and here choose the template. You need to choose one of this application, one of the 5 currently configured. I will choose an example. This is Barflow example. I will just use it as a test that everything works. There are several tabs when you submit jobs. First is the general configuration of application. You need to put parameters here. This is in Polish, at least some part of this application is in Polish, because my web browser is set in Polish, and portal detects the language just from the web browser. I hope you will see this in English. But the first tab is the tab you will work most when you submit jobs. You need just to specify some important parameter for the application. The second tab is maybe not all the second, because for some applications there can be more than one tab to specify parameters, and the number of tabs here can be bigger. There can be more than 3 tabs, but usually one of this is about resources. So instead of specifying all this parameter for Slurm, you need just to specify here what is your job, how you expect, how long this job will run. There are possibility to choose short, long, and standard jobs. Standard jobs is up to 1 day, 24 hours. Short job is less than 1 hour. Long job is more than 1 day, up to 7 days. You need to specify short jobs here. This is enough. You will not run longer jobs here and during the summer school, but it in the background has influence on how the job is submitted, to which queue, to which parameter, which priority it gains, and how fast it will be started. Number of cores you need to specify. It depends on your application. If the application is very simple, just to test 1 core is enough. If you need to specify, if you need to run some real computation, probably you need to specify a large number of cores. And output files. Usually output dir is enough. It means that if you check this, all files in your working directory after the job is finished will be zipped and available to download. And then you can look into this zip file and check results of your application. But in case of something gets wrong, probably you need to get standard output and standard error. They are also included in output dir, but if there is something wrong and you can't get output directory zipped, then you need to specify standard output and standard error that you would like to see these files and check what's wrong. So I can just submit the job. The job was assigned a number 353. It was number here in this portal. And now you can see details about the job, its task, its commissioner, it means who submitted this. It is not important here because you see only your jobs here. You can see to which queue it was submitted. It is standard queue. You can see the state of the job. I will say a little bit about it more. Submission time, estimated finish time is not available here, and I'm not sure if it is always available, maybe only for some kind of jobs. Local ID is the ID of the job on our HPC, on our real Eagle cluster. This is my username, Unix local Unix username on the cluster. And here is where the jobs was started, which was the working directory, in case if you need to look into the machine and check input files manually, but not in the summer school because you will not have access to this supercomputer via SSH. You can refresh the job, or you can switch on automatic refreshment, but I hope the job is already done. No, it's still running. So maybe a little bit about the states. First, the job is processed by portal and it's by some scripts on the HPC. When backend process the job, it's submitted it to queuing system, and then it waits in the queue. Usually, it can be very short, but if the job has some specific requirements and the resources are not available, the job can spend a lot of time in the queue, in the pending state. Then it is assigned resource node and is started. And you can see here the nodes is E0411, and the job is started and estimated finish time is appeared here. Refresh. Still not here, so I can show you on the other job. When the job is finished, its execution is completing. It is completing is the state that means that the job manager prepares output and cleans the environment. Some post-processing, it's just technical step how to process some information from the job, and then the job is done, finished. And you can see all the jobs here on the list. Some are failed. If the job is failed, you can see standard error, some information from job log. Here the information is that this input file is not supported, and in this specific case it means that the input format was wrong. It was just not in the proper input file. When the job is done, you can see standard error, standard output. Of course, if you switched it during the submission, and you can see output directory, process input case directory. You can download all the files. Here this is not possible because there were no output files because the job failed. The job is still running. I will need to check what happened to the job, but oh, it's done. Post processing. You can filter the list of the jobs by its state, by its queue, by commission time, or last update time. If you have many jobs, it is very important to find your job on the list. If you know the number, you can specify it here. Let's check. You can see only one job is here. So I think that's all from the general look and feel of the portal and its functionality. In next days, you will use it not only to run jobs, but run specific simulation jobs, and you will focus on job parameters only and not their technical details. And I hope you will see only green state that all jobs will run successfully. But now I will go back to the slides. Last information. HPC cluster in PSNC is Eagle-Altair supercomputer. Eagle was the first version of the supercomputer with 1,200 nodes with Xeon E5 CPUs. Each of this each of these nodes is Huawei nodes with 28 or 32 cores, 2 CPUs with 14 or 16 cores. Each node has between 64 and 255 gigabytes of RAM. All nodes are connected by InfiniBand. All nodes are Huawei nodes. Some of them are Broadwell processors, some are Haswell processors. But in 2020, this HPC cluster was upgraded to Altair supercomputer, a new name because the power increased dramatically from 1.3 petaflops to 6 petaflops. And the core of this Altair cluster are 2 CPU nodes with 48 cores, total number of cores more than 60,000. And RAM is also bigger, 192 up to 384 gigabytes of RAM. Probably your jobs will all fall into very simple nodes, probably the one with 28 cores, because you will not specify any specific requirements. So probably the first available node will be assigned to your job. Probably it will be Huawei Haswell node with Intel Xeon E5 processors. It is more than enough to run test and example jobs. We have also GPU nodes. So far only 20 GPU nodes, but we are upgrading it now, and in a few months we will have much more GPU nodes. It is our plan for this year. So how you can use SaaS portal? The registration is 2-step. First step, you need to register to the portal at EoCoE. When you will have already the account in the portal, you will be possible to see templates. You will be possible to set up parameters for the jobs. Maybe even maybe not maybe, but definitely will be able to specify resources and input files, but not run the job. When you click submit, the job will fail because it has no access to HPC yet. So if you register to the portal, please write your name and the email with which you are registered to the portal in this document. I hope you can see. Just put the address in the web browser. It is not very long, so it's easy. And then the second step is action on me. I need to assign HPC account to each registered user. So please do it now. Please register to the portal, and please put your name and email and the institution in this document. In case of any problem, you can send me an email to this address. So maybe one information yet, the accounts will be available this week. So you can use it on 3 days of this summer school, and even 2 days longer, up to Friday. If you would like to do more tests, submit more examples, you can do this up to Friday. At the end day of the Friday, I will deactivate all accounts. You will still have possibility to see templates, but you will not have possibilities to run jobs. And after some time, the jobs will be, not the jobs, but accounts will be also removed from SAS portal. Okay, so I will. So now this time, technical part of the session, so the time for registration, I will check if people already registered, and I will assign accounts.
Okay, maybe you can show the portal, the register to the portal. Okay. Okay, after registration. Okay, thank you. Are you moving to another presentation?
In fact, not. This was the presentation about SAS portal and how to use it, and now it is part of technical setup. And the next presentation will be about ESIAS-met by Yen-Sen. So let's just wait while people register. I see the first account registered, so I will assign access to, I grant access to HPC.
Okay. Okay, so we ended earlier. On the agenda was written that your session was till 10:45. Okay. Then we should have the break. Yes.
I was sure that the presentation is up to 10:05. Okay, 10:15, because SAS portal and conclusion was the presentation was split in the agenda on 2 parts.
Yes. Maybe is it Agnieszka? Otherwise, we can leave the people to register to the portal, and you give them the access, and then we will meet here later.
Yes, I'm not sure how to show the address of the document because it was on my slides, but I don't. It's. I'm not sure if you can still see my slides. The last slide.
Yes, now I can see your slide.
Okay, so that's good. So you can see still address of the portal and address of the document.
Yes, I go there. I can try to register myself. There is the login, then a page where I can register. Okay, I started the registration. Now an email is arriving to check my email. Okay, I see already a couple of students already registered. I invite all the students to register to the SAS portal now. So please go to the SAS portal EoCoE.pcnc.pl. I'm still waiting for the email from the portal for the check of my email. Please, the other students start connecting and registering. So you are ready for the next lessons.
Check your spam folder, because sometimes emails from portal fall into spam. I'm not sure why.
Mm-hmm. Okay, I check for that. Yeah, it was in the spam. Indeed. But I think that there is a deadline in 5 minutes. So I have it expired, so I have to register again. Oh, yeah. I have my name in the Excel file. Do you have issues No, the student, or the students. Maybe if they want to if they have some questions or want some more information about that.
I see 2 more students registered in portal, but not as added them to the Excel file.
Any question from the students?
See, Max and Claudio registered and confirmed their emails in the portal. And the third is Serena, also registered. To go. So 5 accounts already configured. 2 more students.
Okay.
So all 5 people that are already in the document, and I assigned accounts can try to submit and test job and to see what will happen. Probably the first job can fail because of some missing parameters, but at least you can see if submission works.
So the students from this morning session are now registered.
Yes, I see two more, Claudio Ronchetti and Avad Shalabni. Claudio is still on the list of participants on our meeting. Okay, I will add Claudio here because he is registered and he is participating in the meeting. Okay, so I think that we are more or less done with the participants of this current session. We need to check in the next sessions for these three applications if there will be more users, and all users that will come later today or tomorrow or on Wednesday. We'll need to register at the beginning of the session, and I will assign accounts then.
Okay. Okay, we can have the break now, and see you at 15 past 11 with the presentation of with the lesson of Yen-Sen. Yes. You have the agenda? Yeah. Yen-Sen Lu with the lesson crash course on weather forecasting. Is it okay, Yen-Sen?
Yeah, no problem. I'm here.
Okay.
So see you. Yeah, 11. Yeah, past 15.
Past 11.
Yeah, positive.
Okay. So thank you very much, Pavel, for this introduction to the SAS portal. As soon as we have more the other students, we will invite them to register to the SAS portal. If we ready for the hands-on today, tomorrow, and the day after. Okay, thank you very much. See you, everyone, at 11:15 for the next session. Bye-bye, see you. Okay, thanks. We can leave the agenda online. Hello. Hi. Okay. Okay, you can try to share your screen.
Yes, I'll try to do that. Yeah, can you see my desktop?
Yes.
Okay. And also the first page of the slide.
Yeah, great.
Okay, then I think you can. Do you want to do an introduction firstly?
Yes. Just a minute.
No problem.
You can wait for a couple of minutes. Okay. So you have two sessions.
Yes, or even 3 sessions.
Okay, 2 sessions, 1 hour each. Okay, the first one is crash course in weather forecasting, and the second is a tutorial on weather forecasting applications. Then we will have the break for the lunch, and then we will meet again. Okay, early in the afternoon for an hands-on on SAS portal. Okay, that's great. Okay, the session is we are registering the session, so it will be available in the next days on YouTube boards. Okay, I think that you can start as soon as you are ready.
Yeah. Okay. So, okay. Sorry for the date. It's 6th of June. Anyway, yeah. Hello, everyone. I'm Yen-Sen Lu. I'm from Taiwan. Did my PhD in Germany in the University Bonn. And today I'm going to give you some crash course in the weather forecasting, and also some how we do this weather forecasting with the the weather program. And first of all, here is the outline. So first I will do some little introduction to bring your eyes on. And also I will give you very, very basic theory of fluid dynamics, and also some computational fluid dynamics, and also some very basic theory of Earth system modeling. And all of these are related to the weather forecasting. And I'm doing this because my original background is in civil engineer. And then I do some groundwater stuff and also do this with the groundwater and the land atmospheric interaction in my PhD. So I understand if some of you is not in the field of Earth system, or even in the for the weather, and that's some kind, we need something to bridge the knowledge between your basic knowledge and the Earth system modeling. So I think most of you know we have this weather forecasting system or applications everywhere. Like for example, this a snapshot from Windy, and you on this side you can check the wind speed or the precipitation. I think that's the most important if you want to avoid some rain, or even you want to have some snow in the winter time. There you go to this website to get the information for a better day. So anyway, there's another application for the weather forecasting. For example, the typhoon. This is a typhoon Sutherland, which approached Taiwan near, I think, 2016 or 15. Anyway, it was well structured. And this picture is taken from the International Space Station. And the media claim this is a really well structured typhoon. And it's quite powerful. And anyway, fortunately, it does not cause a big casualty in Taiwan, even though it just came to Taiwan directly. However, the limitation for weather forecasting can be seen here. For example, this is the most one of the most disastrous typhoon event in Taiwan. On the left, it was forecasted something like 1 or 2 days before when the typhoon event happened in Taiwan. But however, on the right-hand side, we can see the actual path of the typhoon center. It just directly hit Taiwan and in the center, and you can even say that it stayed in Taiwan for some long time. And it brings 1 year precipitation in 3 days in Taiwan and caused a really big casualty. And especially there was a landslide happen in the village, in the mountain, and caused more than 100 deaths. And the whole village is buried by the soil. And yeah, so that was quite tragic. And so that's why we try to improve the weather forecasting, because we can see the limitation. Even though if you use this the website from the Philippines, they record all the prediction from different agencies like ECNWF or GEFS, and you can see this path always change before the real time, because we still have this limitation in prediction. So in order to get the weather information, we have several ways to measure the weather. Like for example, we can see there is the cloud image from the satellite. We can get a cloud information from satellite to get some more comprehensive estimation to the weather condition. And also by the satellite, we can also even get the profile of the atmosphere. So for example, before time, maybe we use this the weather balloon. It will just fly upward to the atmosphere and even to the stratosphere, and then we get this profile to understand the temperature profile and pressure and so on, and also the humidity. But anyway, this is quite expensive. You release the weather balloon, because you can just release one time and just in one point place. But with the satellite, you can get the data more widely. And now we also have this radar by this reflector from the atmosphere, we can get the information for the precipitation after they measure this water particle in the in the atmosphere, and you can know, okay, there's a, like, for example, the cloud with a high precipitation or high amount of water approaching, and you can try to get a better estimation to the weather condition. Also, we have this weather data from the weather stations, and to have a record on it, and then can provide for the future studies. So after we get this weather data, or we also have this geodata, like we need this topography, then soil or vegetation condition on the ground. And then when we get this data, we can use all this data into the simulation software work. And by this calculation, we get some simulation results for analyze, and after analyze, so we can do this for the climate study or provide this for the decision makers, and also for, of course, for the weather forecasting. And one very important thing is like do the visualization, because what we really get is only the numbers, and what's the only useful outcome sometimes is based on this visualization to get a quicker estimation on the weather condition we have simulated. So yeah, let's get into some interesting parts like for the equations, but more of, we will say for the conceptions. So I think the most things that root from the continuity equation. So that's what we use for this. What we're going to do with the continuity equation is just like the really basic conception everyone knows, the mass conservation. So we know how much mass flow in and how much it flow out, and we can get the residual in the one single element. And so by this, and also in this continuity equation, we can also calculate the internal increase or decrease. For example, when vegetation, they extract the water from the root and emit to the atmosphere, we can think it is a source, some kind of source inside the element. It will just produce the water, or in some cases, like for the chemistry, you can calculate the chemical reaction, and there's some more things produced in one element. And this will, and in the continuity equation, everything is driven by some kind of force. For example, for the groundwater, it will be driven by the gravity, and also the capillary force, which you can move the water a little bit up to the upper soils, or to as like the pressure head, and this pressure will drive in the things with its a gradient. So this seems very simple, but when we talk about in the fluid dynamics, or we said in the fluid in the atmosphere, we can think of this Navier-Stokes equation, which complicates almost everything. For example, you have to consider the stress on the element, and also consider the energy fluxes, because when the air mass moves upward or downward, there will be some kind of increase in the loss of the energy. And also, we have to also consider the Coriolis of force, and which will, when I take my atmospheric course, the mentor just said it just destroy everything, because you have to consider this when Earth spin is on itself, and that's why we get this seasonal wind, or why we get a typhoon. But however, the problem is how we solve this. You can see that is a really huge equation, and apparently we know if we want to solve equation, we can just derive it, or we use some like a Newton-Raphson method to find the root of a function, and especially when it's the polynomial equations, we can do this easy because maybe we just want to solve the equation with the only x. However, in the atmospheric science or in the fluid dynamics, it's not the case because we have to consider almost everything: the density, the pressure, and sometimes maybe even the temperature, which also have an effect to the things. And then we will use some method to solve these things. So, for example, this is there are some also use a method like a finite difference method. And in the finite difference, we just consider each grid cell. They are like the mass center. Like we just consider one point move to one point, and then by this finite difference method, you also have to solve the equations, not just between the two grid cells, also with the boundaries, because the boundary will have some. You have to consider boundary as well. For example, if the boundary is a fixed, like it was just fixed, give you the temperature. For example, we can imagine that in the on the CPU, the CPU will always give you some heat, like 80, no, 80 is too much, like 50 or 60 degree, and it will provide the heat, and you need to put this as a fixed boundary. But also, like you can imagine in the bucket of the water, the boundary does not provide anything to like increase the mass of the water, and it will just to fix there, like there's no water outflow, and all of this you need to use solve this equation between the boundary and the grid. And and another is the finite element method. It's which is also widely used to solve this three-dimensional grid cells, and with this irregular grid cells. Okay, but for most of the case, we use the finite volume method to solve the fluid dynamics. So for the finite volume method, we need to generate the grids, as we see before that even it's irregular or regular, this is all fine with the finite volume method. And then you will do some discretization of the equations, and to get then you can calculate this with small pieces. And then we need to do the solution for the equations. It's quite complicated, and frankly speaking, if this should be like a 1 or 2 semester course, but it would be fun if you can find some crash course on it, but just complicated. So why I talk about the computation of fluid dynamics? Because in some case, there's some knowledge will help to understand the simulation. For example, this the Courant-Friedrich-Leavitt number. If you do the CFD, you must know this. But if you don't, this is also important because we know there is a velocity in the field. And what happens if your velocity is larger than your time step? For example, I calculate this for 1 minute, but your mass flow maybe very fast.
İyi olur diye düşünüyorum ben de, ama tabii onu geldiğinden beridir, işte 4.2 vermeye başladığından beridir. Öneriyorum, o hiç ilerlemedi.
Hello.
Yani mesela bu konu
I think someone forgot to mute his mic.
Değişmez direkt. Ne kanda şey var, şu kredi yok. O da var ama yok. Asıl değişmez direktif var. Yani bu konuda isterseniz bölüm kurulunu açayım. Aynı kişi aynı
Sorry.
şey. Ama 20 yıldır bu böyle.
Can you move the...
Aerodinamikçiler o iki kredisinde deney yapmıyorlar, ders yapıyorlar. İşte geçmişte bunu hafız da yaptı diye başlayan bir
to see who's. Yeah, thanks. So yeah, and then the problem is you cannot calculate that. And this in my when I do my CFD in the company to program this, this will just the calculation will be not converged, and then you can see a bug there. That's really interesting in my opinion. When you see if you didn't follow the law of the CFL number. So to find the CFL number is I think the basic conception is quite simple. Just like you have to make sure the time step is fit to your grid state. For example, you just need to know how big is the smallest distance of your element and the time step that you want to calculate it. So by the CFL, in most cases, like tune your time step as small as you want, or we say as large as you want, because if it's too small, yes, your model won't crash, but you will take a large resource to calculate it. So if you want to calculate things fast enough, you have to be aware of this CFL number. So then, beside this equation or conceptions, then we talk a little bit about the Earth system model. And this is quite important because in the weather model, we are not just calculating this with the physics in the atmosphere. We also calculate this, so we need to also consider the effect from the land and the atmosphere, or even the ocean. For example, this we can say one of the flagship code in Europe, the EoCoE, which is led by the Max Planck Institute and the German weather service, the Deutsche Wetterdienst. And they try to put this, they will use this model to run the smart system and also to replace as the next generation weather forecasting or climate simulation. And with their plot, we can see that the EoCoE has multiple parts. One is the atmosphere to the land. You can between these two models, the energy momentum, water and carbon, they will exchange it to each other. For example, this evaporation and transpiration, they will produce the water and consume the energy. And also on the land, so we have the emission from the cars or the factory, and also the exchange of CO2 with within the vegetation. And also the ocean will also provide some like the additional information to it, and also some people they investigate the process with in the marine, and also how this the microphysics of from ocean affect the atmosphere. So we move to the right hand side. Then we can see how complicated will be the system if we consider everything. But here maybe we can just start from the solar. So solar will be the main source that provide the energy to the atmosphere, and also from the atmosphere, then we get the energy or the water to the SVAT, the soil vegetation atmosphere transportation system, transfer system. And by this we can say this the basic of this most of the weather prediction model. For these two, and then sometimes people try to include this terrestrial vegetation scheme, because vegetation is a living being, but in the model, sometimes it's even just fixed. For example, the leaf in some model is just fixed by month. Like in the winter, it's almost 0, and in the summer, it's quite high. But it's just fixed by its type, because now we don't really understand everything. So it's hard to put everything into a model. For example, the vegetarian model, you can imagine that outside your window, every plant, even under slightly condition, it has different growth. And even, you know, this the insects, they will affect the vegetation and also the climate. So that's why some people, they try to do this vegetation dynamics to increase the accuracy of the model, the whole Earth system model. But that takes quite some time. For example, if we want to get the initial condition, which is used to initialize the whole simulation, we need to do something like a spin up to calculate to get the initial condition. And then it takes like, for example, if you consider carbon and nitrogen, it takes like 2,000 years of the simulation time. That means that you need to simulate this, simulate the length for 2,000 years and get this equilibrium state as an initial condition. It's quite costly, so you cannot really do that. But now with this assumption, like you assume how vegetation react to the atmosphere, and then we can do the simulation. Yeah. So this is tool I use for my PhD. So you are also free to use it. So yeah, this is how the land-atmosphere interaction looks like. So with the source of sun, you will provide like the radiations, like incoming radiation to the whole atmosphere and also to the land if there's no cloud. But if there's a cloud, the cloud will absorb the radiation and emit the long wave radiation to the ground. And on the ground, this radiation will like, for example, if one object has the temperature, it will emit the long wave radiation as well. And on the surface, we know this albedo, or the reflectance of the radiation backward to the atmosphere. There was some hour of short wave radiation. And also from the atmosphere, the most important mass is the water, the precipitation. When the precipitation falls, it will be infiltrated into the ground. Also, some will be intercepted by the plants and stay in the canopy. And some will on the ground and run as a runoff, like a river or some ponds on the ground. And the water who fail to stay on the ground will be going into the groundwater. And then this the water on the ground, whether it's maybe it's in a canopy or on the ground, it will evaporate back into the atmosphere. And for vegetation, they will extract the water from the soil and then transpire into the atmosphere. And for the land, it's quite important to understand this process, because the evaporation and transpiration is the key who connect the energy and mass flux together, and also make everything complicated. So for the atmosphere simulation, after we get this land, the evaporation, transpiration of the reflectance of the energy back to the atmosphere, then we get this latent heat flux or the sample heat fluxes. And this we consider as kind of a boundary condition on the ground. And up the ground in the whole atmosphere, then we will try to solve this with to get the calculate for the wave drag, and calculate the cloud with maybe in the deep for the deep convection or the shallow convection. And this will create a cloud, and this cloud will also affect the radiation on the atmosphere. And also the wind will create some turbulent diffusion and to also affect the land surface, because this evaporation is also is also affected by the turbulent. And yeah, and in some cases you can also calculate this. We need to understand the atmospheric chemistry, because like for the O3 chemistry, or we calculate like a CO2, how it transport or how it affect the atmosphere. And we can do this with the real case, but also we can do this with the fiction case. For example, there were scientists in England. They do this simulation with for the movie Dune, the planet Arrakis. Then after they calculate this, they identify that actually in the movie or in the novel, the best habitat area is in the pole, because the other thing is the coolest place in the plane or on the plane. But however, after the calculation, they identify that the best place is near the equators. And this is an interesting article. And then if you understand the atmospheric or the Earth modeling system, Earth system modeling, then you understand why they get this conclusion. And that's quite I would say that's quite interesting, and I think it's quite realistic. So in the for the atmospheric simulation, we have to consider all these basic schemes. For example, the cumulus parameterization, it will help us to parameterize the convection, because in most of the case, when your model grid or your spatial resolution is high, this thing can only be parameterized. It's not that realistic. However, if you can do this with a high resolution, maybe you don't need this, because then you can calculate the cloud or the convection with a more realistic physics. And the microphysics will control the will simulate how the cloud or physics in the atmosphere. And this will also provide some information for radiation transfer. As I said, the cloud will affect the radiation transfer. And these microphysics and the cloud transfer, they will, especially the radiation transfer scheme, they will affect the land surface process, or we say like how much energy to go to the land surface. And for the boundary layer physics, is basically for the wind. So when we have this wind field from the global model or global observation, then we can put this to calculate the boundary condition for each grid. And for this, and it will also affect the surface layer physics, which is calculate for example, the similarity theory. For the similarity theory, and for provide the information to the land surface processes. And with this, we can also connect this to the chemistry, and like to calculate how this chemical particles movement, or to see if this chemistry will affect back to the atmosphere. Also, we can use some module, like involve there's a module like a solar or wind farm modules to calculate the power generated from the solar panel or the wind farm. And also, if you want to want to calculate how the groundwater being affected, you can use this hydrological scheme to connect the groundwater model and the atmospheric model. Yeah, so there's some example for this soil vegetation of atmospheric transfer scheme. Like this is how we calculate this thing with the older variables, especially when we consider canopy, the vegetation on the land surface. And also, we just direct to the right-hand side. So how do we calculate this? This is also we mentioned before, solved by the derivation. So this is we adapt the circuit calculation to understand how these variables affect each other. For example, when energy comes, it will need to be used for evaporation and also for the transpiration, and also like to heat the ground for the to create some sensible heat. And then by this is like a driving force to the whole system, but we need to distribute this to different variables. And so that's we use this the resistance scheme to calculate the final result for the evaporation, transpiration, latent heat, sensible heat. Yeah. And now we go into very tiny stuff. This is called the stomata, the very tiny hole on the leaf. And that's the one control the transpiration nowadays. So, and also the exchange of the CO2, like how much you can absorb or release the O2 or H2O into the atmosphere. However, I mentioned this because the thing is hard to imagine how we calculate this from the tiny pole to the whole atmosphere, because this tiny pole is only micrometers. But for the atmosphere, nowadays, maybe you can do this with a theory. We are able to do this with like a 500-meter resolution. And when we do not, we need to consider this the land surface processes. So this tiny poles is so. However, we need to do that, or otherwise we cannot extract the information from the vegetation, or how cannot see how vegetation affect the atmosphere. So in this, so then we call this process like upscale, like from the tiny pole we upscale to the whole canopy, and then even we can say we upscale this to the whole grid cell. So you can say that that's the limitation of the simulations. Like for some people, they were thinking like, yeah, there must be some effect. Even some people want to calculate this with the quantum for the chemistry reaction. But in some cases, you can understand that that's from atom scale to the atmosphere scale. And I think that's something really difficult in this era. But however, now I think the best we can do now is like to calculate these tiny poles, this stomata, and how they react to the atmosphere, like the radiation and the humidity and temperature, and to see how this how the atmosphere will be affected. And in our in my study, I'm in my PhD, I do the research on this thing, and it really has some big effect because of this. If you use a different assumption, parameterization, it will affect the atmosphere and the groundwater simultaneously. And also because the energy partitioning, it will also affect the sensible heat on the ground. So everything is connected together and very complicated. So that's why I need to talk about this in the beginning, because then actually for these major models, sometimes you just press you just execute it and you get a result. But the problem is how you identify if the result is correct, or how do you tune these simulations, or how you get the information you really need. Yeah, so here's some outlooks. Like there's some unsolved problems. For example, the physics in the weather model we use here, the Wolf. He has multiple physics option from different institute or university, and that means we are still trying to improve everything. For example, the microphysics or boundary layer physics, or even and the length of processes. And another thing is like we want to calculate this with more realistic simulation. Like we need a convection permit simulation. That means when we have a really high resolution of the grid cells, and then we can avoid some unrealistic parameterization, which might be a good solution for the simulations, and to see how true it is. And also the vegetation response to atmosphere is also one of the major topic, like the stomata. And people try to like even argue to each other to which stomata response, or if it's a mechanism enough, or can it capture the mechanism of a photosynthesis, or do the CO2 assimilation. This is quite interesting, but still under progress. Sometimes you can see some equation they change from time to time, or just in one model. And also we need to understand this land atmospheric interaction, even by how this been affected by human. For example, when we have this high development in different countries, we can see the land use change, like from the farm, the forest to farm, or the grassland to the city. And this will all affect the land atmospheric interaction. And sometimes in this case, we need a really in-time information to get then we can get a real real conditions. For example, if you use the land use type 10 years ago, maybe it does not fit nowadays, because in some place they just develop into a big city, or some lake is shrinking, and then they will increase more lands, and with more lands, the interaction is quite different. So if we increase the spatial resolution, there's a lot of digital twins project. Like for example, in ECNWF, they have this Destin project to simulate the whole Earth with a 1 kilometer resolution. And then with the 1 kilometer resolution of Earth, then you can have a really realistic result for like decision makers, or to understand the climate process. And now, but if we want to do this exciting work, the most important thing is the computational resource, because to run this simulation, even you use we call this exascale, you will even take because they want to simulate like the goal is like just for 24 hours of simulation, they want to produce 1 year of data. But this is quite challenging, because first you need to use the computation resource. And I think for the computational team, they can explain more about this, like the connection between the CPU racks, and it's quite complicated. And sometimes you cannot just use the whole resource. Or sometimes we need to turn some the application into the GPU, and then we can use the power of the GPU to do this process to calculate to get the result fast enough. And another thing is the deterministic simulation, and the problem with the deterministic simulation. So sometimes maybe we just calculate this for once, like use this physics and calculate one result. That's called the deterministic simulation. But however, it's not enough, because sometimes you cannot capture the physics we want. For example, the prediction of typhoon is we can see that there are 5 models run it, or 6 models. Well, that means there are 5 to 6 deterministic simulation. But this is all based. That's only if we understand or we can do the real digital twin of Earth. But if not, everything you can regard as some kind of estimation based on a lot of assumptions. So one thing is like, how about we just use the errors from the simulations? We create some stochastic scheme to provide some perturbation in the atmosphere and see if there is some small change to the whole atmosphere, and then we can, with some number of members, we can have some probabilistic simulation. And actually, with this new era of the high performance computers, we have an ability to do that. For example, in my research work in Fortune and Yiddish, I produced like 512 members to get this use all these members to create some probabilistic simulations, or even use it to sensitivity analyze this the simulation with different scheme, physical schemes. So yeah, that's a new possible to do the weather simulation, instead of like you just tell people one number, and now you can tell them some kind of a real probabilistic results. So for the weather forecasting, what you can do, I think maybe learn a little bit, learn some physics. Of course, understand this physics, but I would say that's quite complicated. For me, it took me like 2 to 3 years to really get into this atmospheric physics when I do my PhD. And then it's getting your hands in the data science. So after you get this produce all this weather data, so you need to deal with this data by the data scientists, like how you calculate this to get the statistics results. And another thing is like the professional nouns, because sometimes quite too much. Like for example, in the beginning, I was not really clear what is a latent heat. After a few trainings, and then to really learn this, and okay, this is a latent heat and sensible heat, and how this physics in the atmosphere works. And however, nowadays with the low price of the PCs, like for example, you can buy the AMD EPIC chips with 48 cores. You can even install your own weather model or your climate model in your own PC, and then to simulate them and to see what do you get. And also you can check some open access publication, especially from like the European Geoscience Union. They have this publication through the Copernicus organization. So you get this peer-reviewed, open discussed papers to get information or to see how develop of this geoscience. Also, the GEMS is another a traditional one, but they require everything to be open access. So this we can say is from the United States, the American Geoscience Union. So we have many references to get this information, and then to do the analysis on the data with advanced tools, which will be please show in the next course. So thank you for your attention. And please, if you have some questions.
Thank you very much for this crash course. That was very interesting. So yeah. If you have any question.
Okay. I think it's not this case. So maybe I will invite you to do one thing. It's can you still see my desktop?
Yes.
Okay, good. So now I will ask you to log in the supercomputer system to register something for your to account there, because there's some problem to download the data from the SAS portal. So I would like to invite you to log in the UDOR and to apply the account there. So this is the portal for the from the Fortune Center Yiddish. So you can just do this with sorry, I think I need to find the chat to provide the links to get your account there, and then you can join this EoCoE School. I have already seen 2 people join this EoCoE School, and then you can log in the system and to especially to analyze the data. So where is the chat? Here. So please do the registration there and try to join this project training 2220. Yeah, I don't know why it's a 2220. Yeah, then you can join this number 7 supercomputer in the world. In the top 500. Yeah. So yeah, anyway, it's 11th in the place of 11th, number 11th. So you can still enjoy top 20. So yeah, please let me know if you have any problem to join this portal or to register.
Yes, you can write in the chat, or you simply switch on the micro and ask for help.
Yeah. And also you will apply this, I will grant you the access to the supercomputer. So no worry. I think this can be done before even before the lunch or during the lunchtime. But anyway, I think we take a small break to register it, and then we can go on for the tutorial to use the Word.
Oh, okay. So see you in 10 minutes.
Yeah, I think we start in 15.
Okay, 15.
Past 12. Yeah, no problem. Yeah, see you in 15 past 12.
Yes.
And if you have any trouble or problem to log in, and please let me know, because then you will play with the data in UWells. But anyway, you can still try to submit the job in the SAS portal and to play a little bit, because maybe you are not able to download the data. It was a problem last week, and it's still not solved yet. So let's see.
Okay, so please everyone, you have the link in the chat, and then there is the password.
It's not a password, sorry. After you apply the job, you can ask to join the project.
Ah, okay. Yes, that's the project.
Yeah.
Okay,
Yeah.
fine.
So maybe I should give a little bit demonstrate on it. For example, this is my account. You can see I joined some projects.
Ah,
and
okay, yes, yes.
You can hear there's a small, why is so tiny? To join a project, just press it and to give a project ID, like the training, and then maybe you can refer you from EoCoE project, and this will match to me. That's fine. Then they press a join project, and I will grant it you. And it's not just use the supercomputer. It's more important to use this the Jupyter on JSC, the Yiddish supercomputer center, because for a typical weather data, it will be gigabytes, and I don't think you guys want to run this on your own computer. If by the SAS portal, maybe you produce the test files with 100 megabytes. But if you buy this Jupyter, you can deal with things just on the supercomputer. And I will also provide the links to the data. For example, here, I will have some data there, and you can play with it if you want. And then I will also tell you how we run this in the next course.
Okay, thank you.
Yeah. So yeah, maybe I will start the next course in 4 minutes.
Okay.
Yeah.
Have a coffee.
Yeah, have a coffee.
See you in minutes.
Yeah,
Bye.
see you in minutes. how's everyone?
Okay.
Yeah. So then I will start the next presentation about how we really do this with work for ESIAS-met. So yeah. So why I say we play this work for ESIAS-met first to be easy, and then sometimes we need to be
Yeah, that's sorry that something's changed. Your microphone is not working as good as before.
No problem. Yeah, it just went. Hello, can you hear me?
Yeah, now it's better. Thanks.
Sorry, it's okay. Thanks too. So so let's start with the tutorial for really do the simulation. So we can say we play with this weather forecasting model because it's actually a bunch of name list and configuration and things to deal with. And I would say it's really hard to fully understand the whole model because too many knowledge is required to if you really want to do best the simulation. But anyway, we can still do the simulation with these tools or these programs. So firstly, so I will briefly introduce you to the worth and ESIAS-met to this. The worth is and the full name is weather research and forecasting, and then is how we use the worth to do the weather forecasting, and then is how we analyze the data from this simulation outputs and some outlooks. So firstly, worth is most I think the most widely used weather forecasting system around the world because it's an open source. So that's why I say everyone can install this weather program in your own PC. And also, it has a very strong community. So basically, if you get problem, you just went to its a user forum and you can get support. And even on the Google, if you know the Chinese, and even you can Google some discussion about the worth and how you run it and how to fix a bug in Chinese. Yeah, and this model is I think it's a many developed by the National Center for Atmospheric Research in the United States, and also cooperate with this institute and facilities. And so anyway, in now they even try to upgrade the worth into the MPAS system, which in my opinion is quite similar to EoCoE. Like they use this the EoCoE grids to calculate the Earth system without not with the rectangle one. So for the worth, there's a basic include to manpower one of the worth preprocess system, and the worth itself for the executors. And for the this worth preprocess system is quite important to transfer some data into the data that is readable by the worth itself. So firstly, we need to some input data and use this worth preprocess system to produce this the initial condition and boundary layer condition data. And another name list. Name list is used to control the worth, and then after we execute worth, you get the worth output. And with worth output, as we said, there is some you can connect to something else like with hydro to connect with the groundwater simulation, and with a worth fire to calculate the wildfire, which are quite a disaster for the previous years. And also, if you can also calculate it, so the solar result with the world solar, and to get the information from the world solar. But in our project, we have this cooperation with the Fraunhofer Institute. So we use their system to calculate the solar power and the wind power, but that's their own code, so we cannot do it here. And also one important thing is this world data simulation. So now, because all this from the Earth model system, you can regard as a highly non-linear system. So sometimes we use this data simulation to increase the correct accuracy by we input this real variable like the temperature, soil moisture, anything else you want to put, and then to get the real more to adjust the weather results. So and then ESIAS-met is the system we use to do this for this the large ensemble system. So basically it's done by Jonas Berndt, who do this for his PhD, and to modify the words into a ensemble system. So that means just one executor can produce hundreds and thousands of the results. And this is his one of his results. Like he used 1,024 members to produce this. You can probabilistic simulation, and this also compared to the real data. But why we do this? Why can't we just run this one by one? It's not really good for the environment of the HPC, because if by doing this you are some kind of farming on the HPC, that means the whole system is you will put all your jobs. There's your name everywhere on the system. Like you submit like 1,000 of jobs, and it's not really even healthy for yourself, because maybe you need to wait 2 or 3 days, even 10 days to get all the job done. By this system, they will produce like the maximum was like 2,000 simulation results for once. So that's the really improvement to the world itself. But however, there's still some problems, because he modified these MPI layers in the world. So something related to MPI to world, for example, if you want to have some kind of the asynchronous IO, which means you use additional CPUs to deal with the input output of the data, and instead then to avoid waiting too much time for calculation, because you don't waste time waiting this data is written on the disk. However, this function is not it's an interfere. So, but however, it's still better than you run the simulation individually. So actually, the major difference between the two systems is that the words will be just in a single run. So it will produce a single initial condition, single boundary condition data, and then you just use one single named list to control words and get one output. For the ESIAS-met, you can say that you can have multiple initial condition data, boundary layer data, and use multiple named lists to control words and produce multiple words outputs. And this is really convenient, and especially if you want to do some kind of sensitivity analysis. Yeah. So this is how a real simulation workflow be done. So firstly, we will have some global weather data and the terrestrial data input to the world's preprocessor system. And after the process system produce multiple initial condition and boundary layer conditions. And this will be used because in some global weather data, they can also have the stochastic data. So if some perturbations, or maybe you have 10 members, or even you can use from different agency like the NCEP. They have their own global weather data and the data from the ECNWF to have a multiple initial and boundary condition. With multiple named list and multiple parameters files, and you can run this ensemble version worth to get a multiple worth output. With this multiple output, we put this we calculate it as with a statistical result, and even with the probabilistic result, and we can put it into the wind power management system and the solar power system to calculate how much wind power be calculated and how much solar power being calculated. So in a worst preprocess system, this is how it works. Or even, I think this is also similar to the weather system in the Deutsche Wetterdienste, the German weather service. First, you will get this global weather forcing input from like GFS or GFS from the NCEP, or the ERA file or intern data from ECNWF. Then they will transfer this data with this ungrip executor to get the forcing inputs. It depends on the different type of the forcing input. Anyway, you produce some forcing inputs. And then we need some geo inputs, like we said, this land use or the leaf area index, soil type and topology, and to produce some the needed geography, the information data, and then get this informations and for the MET grid. And by the MET grid, we can use it to produce the meteorological input for WRF. So before you run WRF, you need to do this. But however, there's some different module in WRF, like you can do some kind of the large AD simulation. And maybe they don't really need the global weather forcing inputs. But however, maybe you need to still produce some boundary layer or initial condition or the topology data for it. So after now we talk about what the executor of WRF can do. So for this weather forecasting simulation, what we need is after we get this meteorological inputs for WRF, we also need to prepare the name list, which is used to control the WRF and to provide the information which physics you need and which boundary condition, boundary physics you want to use, and the CFL number and the time step. And also there's some original physical parameters for WRF, and these are all used for the simulation. And first we'll use the real executor to produce some real field for the WRF. They will have some inputs based on different grid resolution. For example, you can, in the first beginning, we will calculate the simulation from the global. So sometimes we will use the grid scale as big as, sometimes only a little bit smaller than the global data. And then we will nest it if you want to calculate German or Poland, you need to indicate which place you want to do the calculation and how big is your domain, like the whole Poland or the Poland with ZEC and anything, and with a different resolution. And in the end, maybe you can calculate your city with a 1 kilometer resolution, then we'll have the third nested domain. This is how the procedure goes. And then we use also the namelist and physics parameter to input to the worth executor to produce the worth output. And if you want additional outputs, and you can do this with the registry files. But this registry file is more related to when you build the worth. So building worth, install worth on your own computer or on the HPC can be easily done with their instruction on the website. And I think it's another, but this is not a main point here. And on the SaaS portal, this is installed by myself and with Damian, the manager of the portal. So it should be, yeah, you can easily run the thing on the portal. So this is how we control the worth for the namelist. First, we need to, something was wrong and was not saved. Okay, so first we need to control the time. So it will not show here because it was blocked. And like control how long you want to run and how and what's the time step and what's the output and also the input. And then we turn to the this domain. That means how much the time step for each calculation. And the domains, you have the one domain here because I just calculated the European with 221 grids and the boundaries, and the vertical for 50, and to indicate how much from the grid levels from the meteorological input, and also how much soil layers, and also the resolution of the simulation. So it's based on the meters, and this is all set up to indicate the domain, and it's and this all can be found on the worth instruction webpage. And then is how you decide the physics. So there are a lot of options to choose your physics. And then you have to indicate here and to say if you need to have the surface flux or if you want to see the effect from the snow. And this all can be tuned here in the physics. And then is the parameters. And so this is the original parameter which only indicates for each type of the input data. For example, the first one is a sand and the second one is a loamy sand, and you can get this saturation point or the maximum soil matrix capacity, these kind of things, and the wilting point, and this is based on this sand information. But maybe you can also argue that the sand won't be the same everywhere. Yes, you are correct if you think of that. And then that's why sometimes we need this kind of digital twins to support this. But however, this is another topic because each area have different sand. How you get this data with one file, then that's another topic. And then is the vegetation, the example is the vegetation parameter. You get this the stomata resistance, or how you calculate or the parameter related to the stomata resistance, and the emission or the LAI. And this is all the information you might need for the weather data. Then that's why we start with the Earth modeling system firstly, because all these parameters affect. But choose the right parameter or to know which parameter might cause problem is also important. Yeah. So if you don't do this with the SaaS portal, and this is what I did with our own HPC with the Slum. So we have our own counter and indicate how much nodes we need. And in my script, I will, first we need to indicate how much like which module you need, like use Intel compiler, and you also need the NetDF for Fortran for the data I/O, and indicate which time I want in this script. And for the simulation, first we need to link the meteorological data, and I link this meteorological data, then run the real executor to get the boundary layer conditions and the initial conditions. And for different physics, you need to run different real. So that's why in this in ESIAS-met, you can run this with multiple initial and boundary layer condition. And then we run the worst executor after you get this boundary layer condition input, and then you can start to produce the data. Then is how you deal with the data. Like I will store this data into one folder. Then you can try to use to analyze the data. And then is then if in most of cases we should use the SAS portal. And in SAS portal, I will recommend you to like run the toy domain. It's a very small, tiny domain with only 64 grids on the boundary. So it has for the mass grid, it only has 63, but it will run really fast. So you can indicate the date and how the starting time, starting day you want to simulate the simulation, and then you can simulate it. Indicate how long you want to simulate it. One like a 12 hour. Actually, don't do that because for the first 12 hours, it will just give you the result after the spin up time. And because like for example the ground temperature is assumed to be like a 298 degree, something like that. And after this spin up time, then every ground with different soil and different land type will have this more realistic temperature. And then you can also indicate how many stochastic and ensemble member you want to run. Like now you can only run 4 because for this toy domain, we only set up like you can run 4 simulations and as a test. And for the stochastic schemes, you can only use 1 escapes, and it's one of the perturbation to the upward wind and the pressure, if I remember it correctly. And in our script, you can also choose different physics setup if you understand what is this are, and you can choose between 6 possible physics set. Then you need to indicate how much resource you need. Like this is a duration of job. Maybe we run this one. It's of course this 1 hour because the toy domain. I think it's produced after 5 or 6 minutes, and you can indicate how much cores you want to run. For the toy domain, you are limited to use only 1 core because you don't need more than 1 core. But if for the bigger domain, like you can see the German domain, but actually it's a European domain. I forgot to set up the nested domain for German. So anyway, you get a full European domain, but you can use more than 1 cores. Maybe 4 or 8, that would be per members would be better. So if you have like 4 members and you want to run with 8 cores, and then you need to choose 32 cores. So then run the simulation is not the hard, but then we need to deal with the model output. For people, if for example, I have seen the result from like the quantum calculation, like using the fastbird, and you will get this text file and get your numbers. And in our system or in the weather, what we get is always the from a grid cell, from grid, as we showed before. So then we can see that each grid cell will define with the dz, dx, and dy, and also the dt. So you must be clarified that so each for the grid cell will start with x, y direction, z direction, and then the time direction. So then you can calculate the things by the structure. So you must know the structure and to do the calculation. But this will be indicated in the NetCDF format. It's not really big deal. So this is just an example of what if you extract the data from the world. This is just the land use type of the North Germany and Denmark. And you can see that they are like a tiny grid cells, but actually it's just 1 point. And by this plot, you'll see it's like in the whole grid cells, but it's just 1 point. You must remember that. And then it's the data position. So basically most of the data will store in the mass grid, that's the center of the grid. And that's because we just get in the end, we just by this finite difference or finite volume method, we get the data in the center of the domain. But if you do this by the finite volume method, you can also get the data on the center of the boundary surface. But however, for the wind, it will be lie on the edge of the grid, because we calculate the wind most from the edge of the we need the boundary condition from the edge of the grid. So remember for the x wind, x direction wind, we also use the u, and the y direction is v, and for the z direction is the w. So for the u, they will have one more grid because for the boundaries, and for the y direction, I also have one more grid. So they have a different grid cell. You must remember. But the good point is that if you want to interpolate the data at one point of the grid cell, for example, if this is the 15,000 kilometer resolution grid, then you cannot use the center for the specific location. So you must shift it to somewhere and maybe just use the interpolation to get the information. And by this, it will be quite handy to get the information of interpolated wind in one direction first, and then you get the wind speed or wind direction in the end. And then this is the tool we need to run the simulation. For example, the one of the most important is the NetCDF, which is I think it's developed from the NCAR, but now they originally used the NCL to read and write the data. But after I finished my PhD, I saw they abandoned this programming language and just encourage people to use Python. And they have this Python module you can import and then to read the NetCDF files. And then by Python, you have multiple data set, the tool to deal with the data. If you use MATLAB or R, and I think that's also okay, because the thing is like if you can deal with the arrays. For example, X array is quite handy if you need to deal with a large data and to deal with these arrays. NumPy is used to do SciPy is used to calculate like a statistical result, or to have faster deal with be faster to deal with the grid cell. And one is some people start to use pandas to deal with the data, but I'm not going to mention that here because basically I just use X array and NumPy, and sometimes I even calculate by my own modules. And another very important thing is this worst Python, because this is the Python module who really deal with the data. For example, previously, we talk about this multi-layer data, but this is now in constant distance, and now it's all in constant distance. Not a constant distance, maybe very small in the close to the boundaries. And then you cannot just get like I want the data from 100 meter height. You cannot just say, okay, let's get the DZ maybe in the third grid. No, you need to interpolate it. So, but by this tool, we can easily to get the variable for diagnosis, and even for the interpolation with a different layer, and to get the data which is corrected after some shifted by the grid cell. And one thing is like the MPI for pi. This is one of the most useful tool in my research, because I always deal with large data. And imagine that if we want to deal with 48 or even 128 time step for output, and then it will be better if you can use this MPI for pi to deal these 128 steps one time, or otherwise we will wait this loop from first time step to the second time step. By this MPI for pi, and if you know how to deal with the data, even you don't need to think of the exchange between the data, and then you can deal with data just all parallelly, just use some high computation source. And this ESIAS-met and Canopy, they are used to plot the boundary or the C coastal lines for this geoscience data, to more easy to identify things. So with the worst Python, this is the direct extract from my code. Like you can get the data like this get VAR. That means they will try to get the data in the Kelvin, the temperature data in Kelvin, and then with this this data you can do the interpolation level at like a 100 meter high. And in other case, like for here, need to extract the data for the relative humidity, and they can calculate this from the specific humidity for you, and to also to do the interpolation on the data. And also, if you want to extract the wind data, you must do this with the this tool. If you don't know how to calculate, but it's quite easy, because for a real the coordination, we imagine that okay, this x and y is just direct to the south, to the north, and x to the east. But in words, because this grid is also coordinated with the longitude and latitude, so it's a little bit shifted. So then actually you need to calculate the, so when he provide you this UV from the model, it's a little bit shifted like this, and you need to correct it with some cosine and sine, and just by the sine and cosine with the right variable, and to match the Earth's grid. So here is some example. Maybe you can try it when you get the data. Like this the data, I compare this with the wind, and with I think there's 600 ensemble members, and to find if the simulation is within the probabilistic or the range of the simulation result can fit into the observation. And in another famous plot is Taylor's plot, and that means that we can calculate the correlation between the simulation and the observation, and also to identify its relative standard deviation, and to calculate the standard deviation to know if it's quite fit to the observation. That means if you have the similar standard deviation, that means you calculate the time quite fit to the observation. And by this plot, we can identify this radar plot, so you can identify, okay, these results, they are more matched to the observation. And then sometimes we just took an instant snapshot. For example, this snapshot from the satellite data about the cloud fraction from the EuroCoE facility. And it's extracted to show that, okay, you can see that this, I think this is above the British, and then you can see there's quite sunny days during there and quite cloudy in Germany. Yeah, and when you can then identify the weather condition during that time. And so when I get also when I want to compare the data, I can also use some technique I took from the land use simulation or the land use science. They try to compare the grid cells and to find if it's over predict, like the cloud is over predict or it's miss, like there should be a cloud but you miss in the simulation, or if it's a match by this by these places. So, but if we want to do some probability this simulation, I would recommend people to use this X array, because it can deal with a large array without creating a lot of loops in your code. It will just deal with this by its own loop and try to calculate things fast. Like for example, if you can set up an array and then you can get and identify its dimensions, and then you can transport it like because I want to do the probably this simulation for each grid cells, and then we can just transport it like put the ensembles to the bottom layer, and then to get the quantile 50 like a median by just on this dimension. So by this method, then I can produce this probabilistic simulation result for like identify like most of the simulation results is tell you like this area is cloudy, and but the extreme condition will tell you, okay, here is more cloudy here. Besides, there's some void. I mean, the clear sky in these areas, and this is done by these tools. I would say very fast and convenient. And also, I can calculate this the total number of the cloud fraction to get this like the within the 25 and 75 percentile, and or the 10 percentile and 90 percentile. And also calculate the root mean square error or its deviation to see its variability. In the simulation, we will always avoid the first 12 hours of simulation. So I don't really calculate the number before 12 hours, but maybe after the post in the latest 36 hours of simulation to get these numbers. But anyway, by this line plot, you can see if the simulation match to the simulation to the observation more. However, this is also tricky because this is a total number of the cloud cloud cover, but you can imagine that if the cloud shift 2 or 3 hours later, then actually you are maybe still get the same cloud fraction above the sky, the whole areas, but the time when you get a cloudy day is the cloudy time is different. So for clouds, it's quite I would say it's quite tricky to do this the simulation or the analysis, because it's better if you can do this grid by grid. But if you do this by your own code, by your own loop in the script, you'll be taking quite a long time. So maybe I can give you some outlooks, like some pros and cons about the worth. Like of course, there's open source with strong support, easy to use because you can get this information from their website online, and the name list and variable description is really clear. But the problem is not a problem. It's quite complicated. For example, you cannot just press execute and run with the name list. You need to use this preprocessed system to produce the data and get understand which this variable means, and to set the proper name list to execute work. So it's quite hard to tune because you need this analogy in the atmospheric physics, and also you need to a little bit for the CFD. That's why I told you something about the CFD and the numerical modeling. Maybe you'll find out why it stopped or it's not converged. And even some physics had a problem with other physics. So you must tune this carefully. But the good news is by the nature of the computational fluid dynamics, you won't really get a problem for converge, because if it's not converge, it will just crash and you won't get any result if you think it's really wrong. But still, you do avoid like the boundary of the whole model domain. For example, for this simulation, I will analyze avoid the boundary of the whole dome, the outer domain, maybe 20 grid cells, and like it. And another thing is some input is needed if you want to run the weather forecasting. You need to get the data from the global weather service like the ECMWF, but you need to pay 100,000 euros for ECMWF if you want to do in the real-time forecasting. But however, if you use the data from the GEFS, and they already provide the data on the portal, and you can just download it for 1 week, something like that, because before you cannot find it. But anyway, everyone's free to use this data and the program. So what you can do, you can try to install it from scratch if you want and play with the GFS data. But the most important to practice with Python to understand how we get to deal with the data, because that's really take time, and sometimes you need some try and to understand how it works. So this assignment is also up. The whole slide is also uploaded to the EoCoE, the conference webpage of this course. So maybe you can try to think about if you can, like let's assume that Hamburg and Bremen, they are compete to build a wind farm. So which location is better for doing it? Maybe you can try to use the data provided in the jewels, and to calculate that specific day, if how was the wind speed, or how do you extract the data there to do this. And then like we assume that Germany is keen to build some more solar panel plants. Show me how you're going to analyze the weather data. Maybe you can run it with this the toy domain, or use the data I put on the jewels. So yeah, so you can try to do the single location with interpolation, and with the Jupyter and the JSC. And also you need to join the you need to join the Judo and apply the account and get into the system to do this plotting. So thank you for your attention, and I'm open for questions now.
Thank you again for this presentation. Very interesting, very practical. So I don't know if there are some questions from.
Yeah. Also put the Jupyter to Jesse, the link to the Jupyter in the chat. So
Okay. Yeah. And also it is needed to register to the Judo at the EoCoE.
Yes. Anyway, yeah. But I will also show a little bit, not just the slides, and maybe let you see how this goes. Like for example, the name list stuff. So yeah. So okay, I think I need to. Okay. I hope you can see my terminal well with a larger font, because this will be.
Yes.
I hope it's not too small. Yeah. So yeah, so this is where we this is a jewels, and this is a jewel cluster. Actually, it's divided into cluster and booster. For booster, you got the GPU and the AMD EPYC chips. But for jewels, you still use the Intel Xeon. But anyway, both are great system, and I also tested our ESIAS-met on both chips, and it's fine. And yeah, so maybe I can show where we run the things. Sorry. So yeah, so first of all is the name list. I think I missed something during the presentation. So yeah, there are digits too for the ESIAS-met. It's for like different, so you can control different members by this name list. But the problem is like you need multiple name list to execute your program. So you must make sure the name list and the number is correct. For example, you must indicate the run hour, start month, end of day. And the interval seconds is for the meteorological data you input. And the history interval is in minutes. So when you deal with the name list, you have to check, because I think the logic behind it is a little bit stretched. Like for the interval it's a second. For history interval is in minutes. And also for the restart interval, that means you can produce restart file for if your system fail, you want to run a very long run, it's stay in minutes as well. So also you to indicate a file name in the history out name, or you can indicate which boundary you want to use. So actually you can use the same boundary or same input for different members if you only have different in the stochastic setup. Yeah. And here is a time step. For example, for each time step, it will be 24 seconds. And to set up your domains and everything, physics, and also some dynamics inside the world. Yeah, so this can, but however, all of this is can be found on the internet from the WOS web page. And here is to show you some stochastic setup, like the steps or some information here. So anyway, this is how we control the worth. And to control its to control worth, I use this like I'm sure you use this script. So I think it is not complicated because the one thing different is I use some Python code to generate a named list. So then I can easily indicate which time or which simulation period or ensemble members I want, and execute it with the setup in the HPC. And for the data, we also do some data assimilation to like we run a really large ensemble simulation, and we can select some members. Sometimes we call it particle, and then the script can be this complicated because I use this script to do it. But however, this is quite similar to the things on the EoCoE, because on the EoCoE SaaS portal, we must fit different conditions, like a different time, day, or different physics setup. So this is audio on the SaaS portal. So then I want to show you maybe just a very quick demonstration of the SaaS portal, but the problem would be we are not able to download the file because the thing is that you must click the file and then there will be a button asks you to download, but the file is big. Even with a toy domain would be 300 megabytes, and I don't think it's a good idea to download them. So anyway, so let me submit a job and choose our ESIAS template. So yeah, so maybe you also see this, the similar with what Pavel has already demonstrated. So you can use it, choose German, but it's Europe actually. And you can choose different months if you want to run Germany. And yeah, maybe you want to run on the 8th of August and simulate for 72 hours, but now it's set to 48 hours. But if we upgrade the script, you can run whatever simulation hour you want. But it was under tested before, so also the stochastic member is only 4 because for each stochastic member we need one parameter file. So, but it will be too big. So let's just put 4 members. In the future, maybe I can increase to several. And these are 2 skins. I'm not sure if PPT is ready yet, but because it just relate to the script. But here it's ready yet. You can use different like GODA, microphysics with its radiation, and or with WSM6. I think this is from the Korea. The team in Korea do this for work. And the YSU, I think this is it's also from the United States. And with this parameter, then different physics, then you can try to submit. For results, for the toy domain, you can only 1 core for 1 ensemble member. But for the German, no, there's no limitation, so you can use like 16. They will divide it with this 4 members, so you get 4 cores for members. Yeah. So then we can try to see, it's submitted in executing. And did I do this with a German domain? Anyway, if it's a German domain, it's executed. But however, one file will be 2 to 8 gigabytes. So sorry for the ecosystem. I just make more data there, but we are not able to use it. Because if you want to use it, you need to like click into it and to go to the output directory. And then in the output directory, you should get the data here. For example, there's the one output, but when I click it, it will show some network error, so we are not able to download it. But however, the name list is generated. This is just one member, and this is the log file here, the ISL. You can check how the simulation works. For example, it will show you the details. Yeah, like what kind of the information input inside and the grid cells information. But most importantly is that when it starts to run a simulation, it will provide you this runtime and the log files. So you can see that for writing, it took, okay, this is a small domain, so it took only 0.02 seconds. But for the German domain or something like that, it will take something like 10 seconds for it. So it will quite exhaust some resources. Yeah. So yeah, this is what if you can do with the SAR portal, but the problem is you cannot get the data there. So anyway, we are able to use the data I generate for the for my research. You can just direct use it. I think no one will oppose it. And you can use the Jupyter in the function center usage. For example, maybe I should do this from the beginning. Yeah. So in the Jupyter portal, you should add a new Jupyter lab. And I will recommend you to use the Jupyter Lab 2 because that's where you get the support for the Wharf Python. And because we use Jewel, so we should use the system Jewel and use the training project. And then you can press the start. Yeah, then it will create a job on it. And then you can start to use the portal to deal with everything you want. But let's skip the waiting time. And so like I said before, what you need is the nested for to read a file and the X array to deal with the arrays. So after you have this type this, you can just execute it. If you get these modules on the portal, then it can be done without any the error messages. And also I use the matplotlib to plot things. And here is the data. The important thing is that also, I think I also put this on the slides. You can get the data here. Like I've provided 16 members there, so you can deal it with more realistic or more practical statistic result. But here I just show for members. So you can read all this data and create the information for dimensions. For example, this is for the X array. Like actually you don't need this one. Like you need to give the array information. It's just a sequence of number, like 222 in X array, and for Y is 220. But for Win, you must be careful because you will need the information there. So for example, but however, if you are not sure what the grid you have, you can just get the data by press to call this object. And for the object, you can get the information like which the microphysics you use and unstack by the how much mass grid you got in the direction of west to east or the south to north. And this stack is for the wind. So yeah, you will get this data here, to get this information there, or you can just get the dimensions. Yeah, so you get the dimensions from like the how many degrees cell you got. For example, I want the where's the east, and then we just want a size, and then okay, 220, and you can use this, even put this here. Okay, and how much ensemble member you got? For example, there are 4, so I just directly use 4, but so you can do whatever you want if you are familiar with code. And I also create a data array to store all the information I want. So this is a 3-dimensional array with ensemble member, X array, and X dimension and Y dimension. So I store the 35th time step with the noon of the next day. It's a cloud fraction. So I just store all the data there, and then I can get, and then I use and I create a array from the X array, like a input the data array I input and indicate the coordination or coordinate, like the number of ensemble and NY and NX, and to give its name. I think it doesn't matter if it's called ensemble or XY, maybe even this can work. And yeah, and then you get this output, and by this output you can transport the X array from the order of ensemble YX into YX ensemble. Then you can analyze the data for all the ensemble members, and then because it's just 4 members, so quick. And I want to calculate the median, so I do this quantile, and yeah, I forgot to change this. So this will take some time because it's use a loop to deal with that. And then we get the data of a median here. Yeah. So we can plot the data here to show, okay, this is the cloud fraction. You get this from median. And for the original data, for example, yeah. Yeah, it's okay. Yeah, see, this is the original data. It's after we deal with the 4 members. If we deal with more members, of course you'll get a more realistic. Go get more information from more ensemble members. And I think in the statistic, over 50 or 40 members, then you get the effective statistics result. Otherwise, with 4 members, actually what we got is the mean, maximum, and minimum. So this is how we're going to deal here. So yeah, I think this is basic I show for our course. So any questions?
Thank you.
You're welcome.
Is there any question? Okay.
Yeah, I think, yeah, the very important thing is to just play with the resource we provide. And yeah, then you will, yeah, to analyze it, like this is a very simple, just analyze 1 hour, but maybe you can try to analyze all the hours or something like that. But let's see.
Yeah, that's very clear. Thank you very much.
Yeah. So yeah.
Okay, it's time for lunch.
Mm-hmm.
Is there any session after lunch?
Yes.
Yeah. At what time is it 45?
Yes, I'm looking at it too. Yeah, it's 1:45. Okay, yeah, a little bit, yeah, but I think maybe we can delay for like 5 or 10 minutes, 5 minutes. Anyway, I will wait online because for the hands-on, it's more about if you have question, I will stay online and then you can start anytime. But I will monitoring the portal to the portal in Jewel to grant you the access to the training project.
Yeah, for example, there is a question from Redwan.
How should we submit KPI to local is possible? Yeah, if you have the counter, yeah, that's the slum. Maybe I can direct show you how we do it. But if you are referring to egos, then you need to submit with the ego. Yeah, I did here. For example, this the folder contain with the word, and I just test it in the morning. So I just go to ESIAS run, and yeah, and submit job with this this system is used as batch to submit the job. Yeah, then it's a submit, and it will start to produce the data in this folder. And then you can monitor if there's something wrong, like in this arrow or in the out, if they produce something. And that's if it is fit to your question. Yeah, and then the data will produce here, then you need to manipulate the data there. But I think on Ego, you cannot do this with Jupyter.
Yeah, I agree with you. That's the first run. Maybe it is better to do together here in EoCoE or by using the EoCoE infrastructure.
Yeah,
and then you can move to a local installation or a local submission. Anyway, we can discuss this afternoon also of this possibility if you are with us later. I would say that at 2 o'clock.
Yeah, I think, yeah, I'll be, yeah, let's go back at 2 o'clock. But any question can be posted on the chat. I will try to answer as much as possible.
Okay, great. Thank you very much. See you at 2 o'clock.
Yeah, see ya.
Bye.
Bye. So hi everyone. So I'm back to the computer. So if any one of you had a question, please be free to ask me.
Okay, thank you. Let's start.
Yeah. So I think I already showed you how you can submit the job on the SAS portal, and you can try it. But yeah, but the problem is that you cannot see the you may not be able to see the how to call this to download the data. But anyway, I will also try to provide you something for the from the jewels. So if I success to deal with the files, like you can just click the submit and submit a job, then I will let you know. Well, otherwise, any of you can ask question freely. So if you submit the job on the portal, you can also try to check the data, check if it's execute and run. But I guess in this case, it's more like because the data is quite large, so it has some time to deal with moving the data in the portal system. Okay. If anyone want to try, you can also try to submit the job on Jubel system, and maybe to test to experience how we do this on the HPC. For example, when you log in Jewels, you will first go to your home directory, and on Jewels you will be have different file system, and mostly you should go to the Scratch to do your works. So yeah, if you have a directory, you should be able to do these things. But let me check if we have a directory for it. Yeah, we have a training 2220, and you can make your own directory for me. For example, I'm do3, and you go to do3, and to copy the data from we have set up for this course. Yeah, you should copy something and run all the things on Scratch, because this how this file system do for, like you store your data in the large data because they won't delete it from it. But on Scratch, this is directing to the HPC, so most of the data should be most of the calculations should be done on the Scratch partition. And for the project, there's also a project partition. That's a store your program, this thing, which can be stay there for years during the working program. So after you copied everything there, can I show you what I did to another folders. So if you already copy everything there will be two folders. One is main, is the executor, and the other is run. In run, there will be ESIAS. There's a script for Slum that deal with everything you need. The modules you should load for run the simulation, and number of the ensemble. Maybe you can run 2, 4, 8, everything you want. Just make sure this all can be divided. The number of ensemble can be divided by the n tasks, which are the CPUs. So in this case, we just run 4 ensembles with 4 nodes. That means every 48 CPU cores will deal with 1 members. And after you, and you can also tune the simulation time. For example, here there's a simulation time. You can do it with a 48, because that's how much data I provide there. After you've done this, you just need to do as batch submit, and then you get all the data. Yeah, and actually this is after you submit the job, you can see the data is produced. And if you want to know how much data it produced, you can do an NC dump the NC netcdf files, but I just require to dump the times it has, and maybe just the first one. Okay, so now it run for like 14 hours. So yeah, then you can get the data for it. If you want to see your data, you can also do a module load NC view, and then do this NC view to your data. Then you can see like, for example, the cloud fraction for each hour. And the skin temperature, if I'm correct, or we just go to the temperature at 2 meter. Okay, there's some errors. Not sure. Okay, because maybe it was writing the data. So yeah, see, becomes 16 members, 16 times that. You can see the data. Then you can start to analyze everything you need, even the downward short wave radiation with it. Yeah, partnership. Yeah. So this is at the October. So the moon, yeah, we get the radiation around like 8 o'clock in the morning, and then we lose the radiation after 15 UTC. Yeah, remember the time here is all UTC. So you can have fun there and to try to submit the job in your ESIAS program. But I will also check if I can also do this with my own folder. Yeah, if you want to check if your job is still fine there, you can do SQ. And according to your account, this is not account the project, this one. Yeah, you can see I run 2 jobs on it. And it seems okay because maybe, but we have to see. Nope, but I know why. Because you need to change to your folder there. Okay, yeah, get my data there. So yeah, I hope you can also produce your own data with different number of sample papers. Okay, we got problem. So let me try to solve it. So I will copy the program data there. Anyway, this project will be end in the end of this month. So we should. Yeah, by the way, I would like to share that this is the script I really use for the research. It's not created for the EoCoE School. So yeah, if you understand all the lists, then you can just try to use the script to create it. even you can use this script for Word itself if you want. And this all the thing I share on the GitHub. So if you don't mind, you can go to my GitHub and to use the tools I share there. Yeah, can see this. Yeah, this is my GitHub, and I think this tool is belong to the Word tool. And for the of this tool, you can create a list, and this then will calculate something like calculate the start time or the run time. Yeah, something like that. Yeah, and also you can use the tool to produce the Taylor's diagram. So if you use the SAS photo, normally you will get the output after the job is finished. If it's not, then will be all deleted. And on the SAS portal, the way we try to identify if there's a problem to go to the ISL. This also fit to the Word. And by this, you can yeah, you can check if everything's fine. Yeah, if success, it will give this tag. Yeah, and you can also identify how long it takes to write the data. So yeah, I think this should be the case. Like you can work with the data I provide from the Jupyter, and using Jupyter to deal with that. Or you can also try to simulate with it on the jewels. Yeah, but you can see each data will be like 2.5 gigabytes. If you want, you can also take it out, but that depends on you. And this data I will meet your friends is the data we try to provide to the other people. So yeah, you can also set up what kind of data you want to extract from the history from the simulation. But just you need to modify a little bit from the regist file. Okay, so it will be a little bit early, but I think we can try to conclude the hands-on and the course. Does anyone have any questions? So seems not to be the case. Yeah. So is anyone still wake up here? Oh no. Hi, I hope I pronounced right voice here. What's the problem? You mean the permission problem? Yes, these all belong to the groups. So yeah, can you tell me what kind of problem you met? That's weird. So you still got a problem with them? You cannot copy that, right? Don't know if this can be fixed by that, but try it. If you don't mind. Okay, check. We can just do it here. Well, hopefully you are able to use them. Okay, anyway, if you still have problem, you can email me, and yeah, here's my email.
Okay, thank you very much. It was a really useful, in-depth presentation of the code of the system, of the software package, how to use it, how to exploit it. So that was very nice.
Thanks.
Yeah, I think that it was very useful. I hope that all the students they can use it and send to him or to the organizer any question, any suggestion. And so I would close here the first day of the school. And thank you again, Yen-Sen Lu. And see you everyone tomorrow.
Yeah.
I think at the same time as today. See you. Bye bye.
Bye.
I close the session. Okay, thank you.
Yeah, enjoy.
Okay, I close the session. Bye.
Yeah. Bye.
Bye bye.